Okay, this is Supplemental Movie or Supplemental Movie Tutorial 1 associated with the Nature Protocol X-ray structure determination using low-resolution EM maps for molecular placement. This is done using 4 tools. The tools are UCSF Chimera. We're also going to use just the command line, the Phoenix on Phoenix with the command line, and then we're going to then use cutout, and then finally we're going to use a tool in the GUI of Phoenix right here. So these all need to be downloaded on your computer. UCSF, you need to be able to have access to both the command line and the GUI of Phoenix, and you need to have cutout up and ready on your computer. The first thing we need to do to prepare an EM map is to convert it from XYZ coordinates to structure factors and phases. And this we'll do using Chimera and the Phoenix command line. So first step is just to open the EM map. Here we go. I'm opening the map here. We provided this as supplemental file 2. And one of the important things that needs to happen for the software to change the XYZ coordinates to structure factors and phases is the origin of the map needs to be 0, 0, 0. This can be easily done in Chimera with the volume viewer. I'm actually going to close it here. It opens automatically with mine, but just in case it didn't open or you lost it somehow, it's found under Tools, Volume Data, Volume Viewer, and then here in the Volume Viewer you click Features, you go to Coordinates, and you change the origin index from whatever value it is to 0. This changes the origin to 0, 0, 0 when you hit enter. You can see when I hit enter, Cascade shifted a little bit. Now all you simply need to do is go to File, save Map As, and save it as a, you just want to give it a file name that you can remember. We use S4 map shifted MRC, and this just indicates that the origin is now 0, 0, 0. So we save. I'm going to hit yes here, and we're now ready for the command line in Phoenix. I'm going to minimize this. So you want to get to open the terminal window, a new terminal window. You want to navigate to where you want the file that we're going to create to be saved. So I want this to be created in the Cascade tutorial file. So find out where I'm at, and I want to navigate to the desktop and my new Cascade tutorial. Make sure that it has all the files I'm looking for. Okay, now that I'm where I want to be to save my file, I need to source Phoenix. So source, and then it may already be sourced on your computer, but I'm going to manually do it here. So we go to where you have your version of Phoenix installed. Mine's in the applications folder, and we're going to use this shell script here because I'm using bash. Enter. And now Phoenix is sourced, it's ready to go. We're going to use the command phoenix.map to structure factors, and then space dmin. Dmin is the minimum density that we can go to, and in this case it's the highest resolution of your EM map. So in the case of Cascade, that's going to be 8. And then the next is the output file name equals what? And then in the case of Cascade, I like to save that as supplemental file 5, map coefficients.mtz. The extension on this file does need to be an mtz file. And then you need to tell Phoenix where to find that file. In our case, it's in this folder where we're at, so you can just navigate to the folder where it is and run it there, or you can specifically tell it where you want it to find it. So I'll just do that here. and we want to do S4 shift, and so you need to give the path to the file and you hit enter. Okay, now that we have converted the map to structure, factors, and phases, we need some information that we're going to use later on. So to do that, we need to open the map in cutout. I'm just going to minimize this. We're going to open cutout. So I'm going to File, Open MTZ, and we need to navigate to where we've deposited the newly created MTZ. That's this S5 file that we just created. Open. And what's interesting here is that it looks like nothing opened. So if we go to Draw, Cell and Symmetry, and we want to show the unit cell, hit Apply and OK. Oh, okay, so something did open. So this is not uncommon to have this problem where you don't see any density. And the reason why is that the EM map is now not located, it's not located at the origin. I'm hitting the control button and I'm just the left mouse click to navigate in cutout, but the density is actually found right in the center of the unit cell. So now you can see where, but you can scroll up and down to show different contours of the density. And you can also change how much of the density you show by going to Edit, Map Parameters. We're going to change the map radius to 150. It's going to eat up a little bit of my CPUs, but hopefully it doesn't take too long. Okay, now that we have expanded the map that we can see, what we want to do is define the center and the extents and the X, Y, and along the X, Y, and Z axes of the cryo-EM map. And so the first thing we want to do is define the center using the control button and the left button on the mouse. Push both of those and you can navigate through the density here. And you want to basically try to, I back out, I try to look down one of the axes, try to get it centered that way, turn it 90 degrees, and I think that's pretty much the center of the EM density. And then what I'm going to do here is place a water molecule at the cutout cursor. That's done by using this tool right here, place atom at pointer, select water, OK, and then if I middle click on that water molecule, it shows the position of the center. And I guess what we'll do is write that down in a text editor here. Center 65.84, 166.27, 168.25. These values are going to be important for the cutout density tool and for phaser later on. Okay, now that we've placed a water molecule right there, we need to figure out the extents of this density. And so if you look up here in the corner, you can see that this is the y-axis and this is the z-axis. What I'm going to do is use that control button, scoot up to above the density, place another water molecule there. Now I'm going to scoot down to the bottom of the density, place a water molecule. Now I'm going to go to the sides. And to this side. Now to define this extents, I'm going to use the measures tool, distances. And I'm going to click on that molecule and then click on this molecule, or that way. And it will tell me the extent of the y-axis. So the extent of the y-axis is 184.85. So I'm going to go over here, 184.85. And then I'm going to measure this distance on along the z-axis. That's going to be 196.01. And then to get the axes of the x-axis, we need to turn the unit cell this way. And by now you should have the idea of what to do. We're going to place a water molecule here. And we're going to place a molecule over here. And then using the measure distance tool, we're going to click on these two water atoms that we placed. And that'll give us an idea of what the extent of this axis is. Looks like it's 185.50. .50. Extents. Okay, so now I have the center and the extents, and these are needed in the next tool. And I don't need cutout for the time being, so I'm going to minimize it. Close these down. Okay, so the final thing we need to do is prepare this MTZ file, these structures and phases, for phaser. And what needs to happen is that the structure factors and phases need to be placed in a P1 unit cell that's 3 to 4 times larger than the original EM map. So we're going to do that using the cutout density tool in Phoenix. You get there in the Actions tab under Maps, and then we're going to use the cutout density tool. Here we're going to load the MTZ file that we created using the map to structure factors. That's this supplemental file S5. We're going to leave these fields blank. We need to make sure that the output directory is where we want the files deposited, and we're going to give it a job title so that we can remember what we're doing. So I'm just going to say cut out to large P1. The map labels are going to be selected automatically. Those look like appropriate map labels. Cutout type is box. The output resolution will be the resolution limit of, or actually slightly under the resolution limit of your EM map by about 0.2 angstroms. The padding around the density here is the first place where we're going to use this extent information that we just found out in cutout. You take the value, the largest extent value here, and put it here in this padding around cutout density. So 196 should be appropriate here. Here we're going to put the center of the EM map. So these values that we determined in cutout. So that's 165.84, 166.27, and 168.25. The cutout dimensions are going to be the extent values. So 180, well, we can round here, 186, 185, and 197. The cutout sphere radius and the cutout model radius should just be left alone. These actually don't matter when you're using the box cutout type. And now we'll hit run. The program should finish in less than 5 minutes, and this is actually finished. The results window will pop up that will have the new MTZ file of your electron or of your map density in a much larger P1 unit cell. We want to make sure that this worked before we end the video here, and the way you do that is open it up in cutout. This is going to be a very big file, a very big map, and so I'm actually going to reduce the map radius a little bit here to 30, and then I'm going to open the newly created MTZ, and so here it has a cutout density folder. This is the new MTZ file. And it's opened the new map. I'm going to come up here to Display Manager. I'm going to turn off the other density, and we need to draw cell. This is going to help us find the newly cut out density. So if you look, you can see that it's a very much larger unit cell, and when it does, when the cutout density tool places the new density at the origin, and so if we move to the origin here, we should see the density as we move close to the origin. So there is the newly placed density, and we want to make sure that this density wasn't cut on any axis, so we're going to edit the map parameters. We'll go to 100 radius, and you take a good look at it and make sure that it doesn't look like it's been trimmed along any axis. It looks pretty good. So now we're ready for the next step in our protocol, which is using this this prepared map in molecular replacement.